Okay, so today we're going to be looking at more space curves. And I'm just going to make one up here. Okay, whatever. Okay? So, as you know, we can do the derivatives with that. I'm just going to get the calculator out and go ahead and do that. And I guess while we're here, we'll go ahead and review a little bit about the tangent vector and the normal vector. Okay? Because you got to run past them again anyways. So here we go. Right, there's A. So I take the derivatives now. Take the second derivative while I'm at it. Whatever. Okay. So I could come up here and find, for instance, the tangent vector is this guy. I'm just going to go ahead and do this guy dot itself, which I forgot to put the dot out front, so allow me to add that. Dot product. Oh, before I do that, let's put a square root in front of that. Whatever. So there's that. And then, of course, if you do this guy divided by this guy, okay, there is your tangent vector. Okay. Now, again, I probably wouldn't do it that way. Yeah, I probably wouldn't do it that way for evaluation purposes, but I did it this time because I did. And so, okay, something screwed up there. Let's try it again, shall we? Okay, let's come back up here. The original function was right here, such that t equals 1. Oh, for God's sakes, you're an idiot. There you go. And then, of course, if you wanted to find, so that is my velocity vector. If I wanted to find my speed, I would take the dot product of this with itself. And then the square root of that. At 12 point something. So I'm going 12.16 meters a second, if you will. That's my speed. Okay, that's at t equals 1. Now, obviously, if I take this vector right here and divide by this, this will be my tangent vector, the tangent vector at 1. So 0.98, negative 0.13. And negative 0.09. Okay, that's the tangent vector at 1. Again, to find the normal vector, if I do this right, I have to screw it up this time. So there's my first, somewhere up here's my first derivative. So there's my first derivative divided by oh, for crying out loud, where is it? There, that guy right there. So this is the the tangent vector. Now I'll take the derivative of this guy. Give it to me. Of this guy with respect to t. So this will be, if it ever spits it out, okay, so let's go ahead and evaluate that guy. Again, let's just pick a value. So because we did 1 already, we're going to do that again. Boom. Okay. So grab that guy, diamond enter. Oops. Diamond enter, I said. Oh, shoot. Okay, there it is. So that guy right there, okay, is the top of my normal vector. Because remember, the normal vector is equal to t prime of t is equal to the derivative of this thing, right? It's t prime of t over its magnitude. So what I've just found is I've just found that guy. That's what I found right here. So I found that derivative and I evaluated it. Now that I've evaluated it, I'm going to take it and divide by its magnitude, which is obviously way less than 1 at this point. So that's okay. Diamond enter. Booyah. So that guy right there, when I divide out by its magnitude, again I did that after the fact, that is, again at 1 this time is what I found. It is 0.069 negative 0.153 and 0.98, I think. 0.985. Okay, that is the normal vector at 1. That's what we did yesterday. Well, today we're going to add to that. We're going to find what's called the curvature. And you can spell it with a C if you like, but K is the variable that we use. Okay. What it means is this: if you have a space curve coming along through here like so, at some point in time, let's say you're at t equals 1. If you plug that into your original value, you will find out where you're located. Okay, whatever. Now, what happens here is this. There's what we call the radius of curvature. If you come out here, some radius, you can build a circle that comes across here like so. All right, that radius is going to change when the circle, when the curve is basically almost non-existent like this. It's going to have a huge radius. And when the curve is tight like this, it's going to have a teeny tiny radius. Okay, well the relationship here, the curvature is 1 over the radius. Bless you. Okay, and that's great. So obviously once we find the curvature, we can find the radius. But how do we find the curvature, you ask? Well, there's a couple of things. So first of all, we can look at it a couple different ways, but the easiest way to compute is it's this guy cross this guy, find the magnitude, again at a particular point, so t equals 1, let's say, over this guy cubed. Well, this is clearly speed on the bottom, speed cubed. Any idiot can see that. So really, it's just a matter of finding that numerator. It's the only new part we have to do. Now, you already did that. You already know, well, we already did it earlier, but I'm going to do them again just because I lost them and they're too far up there to go find. So there's my first derivative, right? And then do it again. Here's my second derivative. And then I can do the dot product right there, or I can evaluate them first, whatever makes me happiest. I don't know that it makes any difference to me. So I'm going to grab that guy such that t equal 1. I said dot product, I meant cross product. Are you leaving? Yeah, where are you going?
Hi, buddy.
Leave my baseball stuff.
Alright, have a good day.
Bye.
Bye.
And then And it doesn't matter what order you cross them because you're finding the magnitude anyways.
Are you talking to me?
No, crackhead. So there's that. So there's the cross product. Now I'm going to take the dot product of that, but the square root of the dot product, obviously, right? So the square root of the dot product, because this is going to give us the length of it, with itself. And so it's 20.3 on top. And on the bottom we said it was 12 point something, yes, 12.16 cubed. And so it's 20.3 divided by 12.16 cubed. That. So I get a curvature of 0.01129. Alright, that's nice. What would the radius of this curve be then? Well, to the minus 1, you get 88.5 meter radius for your curve, which means the curve isn't very, it's not very curvy at that point, which is not surprising. You know, if this had been e to the positive t, maybe this has been something a little curvier than that, like if, let's say, a t cubed, then you'd have even a bigger curvature because obviously they're all bending really hard at that point. Okay. If there's a straight line, sorry, a straight line, well, the radius is infinite, right? Which means the curvature would be 0. Okay. So just be aware of that as we go along. Now, where is this going to come into play? Well, it's going to come into play because the tangential velocity is going to be the magnitude of, let's start right, f, r double prime of t, right? Right, in the direction of the tangent vector. Okay, and the magnitude, or the centripetal acceleration. Oops, when did I say that? I meant centripetal. Is going to be, well, remember, centripetal acceleration is v squared over r, right? Well, it's going to be the same thing. What is v squared? V squared is this guy, right? Alright, and of course you could write a v right there, it wouldn't hurt my feelings. It's just the speed squared, so 12 point whatever squared. And then over r. Well, this is the same thing as saying v squared times 1 over r. And 1 over r by definition is curvature. Right? Oops. What are you doing? Times. There you go. Q. So in reality this is going to become this. And in which direction does it point? It points this direction. So then the total acceleration is, of course, the square root of this guy squared plus this guy squared. Why? Because they're orthogonal. That's it. And so we're going to be doing that. It's not very hard. It's a piece of cake, actually. We've already found this. We found this. Today we find this. We already know what that is. We know what this is. You're done.
What?
Now, curvature can be defined a couple other ways as well.
I know it.
Hey, can we, thanks. Can you run up and grab my calculus book? Now, another way to think about curvature, and some people like it, some people don't. Not a big deal to me which way you like it, but you could think of curvature as a function of where you are on this arc length, okay? And what it really is, it's a change in the tangent vector with respect to the curvature. In other words, here's the tangent vector, and what we're saying is that how far are they changing? What's that difference between them? That's the idea of the curvature. Again, you're talking too loud. I'm online. Thank you. Can you shut up? Thanks. Yes, thanks. Now, if you had a y as a function of x, right? Just y as a function of x, curvature could actually be thought of as this. Right? And so, in other words, you want to find how hard, here's e to the x going up like this. Okay, if you want to find the curvature of this guy, a person could do it as well, but it would be this formula right here. This to me is it's intuitive because it's like, oh yeah, it's the change in the tangent vector with respect to this guy here. That's how far apart they are. That makes sense, but you can't really find it that way. The way to find curvature is this formula right here. It is the easy way. That's the way a person wants to do it, in my opinion. I'm going to throw you out on your head in about a minute if you can't shut up. Thanks. Just saying. Swell. Okay, thanks. And so that's basically it. Yeah. So that's that. That's the easy way of doing it. And I hope that helps. Oops, one more thing. This circle has a name. We will talk more about it later. It's called the Osculating Circle. Osculating Circle. Okay. And clearly, as you go down the road, like here, you'd have a giant radius. And as you come into this corner, that radius would be getting smaller and smaller, and then smaller, and then start getting bigger maybe as it gets flatter out here again. Okay? Because that will constantly be changing.